So hello and good evening to this little talk series where Europeans collaborate on knowledge graph research and do not compete for a ball. There's a competing event running as now with some Belgians involved, but here we have a Swiss talk about UniProt and others, fairly large and connected SPARQL in the life sciences by Jerven Bolleman. What is this that you just dialed in? It's our talk series on knowledge graphs hosted by the cost action on distributed knowledge graphs. We've had a few talks already, and after the summer break, we will continue with more. We don't have all the things set in stone yet, so watch our webpage for more talks. Today, we have the talk by Jerven Bolleman from the Swiss Institute of Bioinformatics, and I would like to hand over to Olaf to introduce our speaker.
Yes, hello everyone from my side. So like Tobias says, we have Jerven today as a presenter. He's in the Swiss-Prot group of the SIB Swiss Institute of Bioinformatics and currently in the role as a principal software engineer. And in this role, he's responsible for running the SPARQL endpoint of the UniProt Knowledge Graphs, which has been in production since many years now, I think since more than 10 years. And that's why he is here to kind of tell us a bit about the knowledge graph and about the SPARQL endpoint and so on. So I'll give the stage to Jerven now.
Hi everyone, screen sharing working and not yet. Okay. So
I can see your screen.
yeah, okay. So can I on other monitor? So hi everybody, my name is Jerven Bolleman and I do indeed work on providing the SPARQL endpoint for UniProt, which has been public now indeed for almost a decade, and the RDF since 2007. So I'd like to share some lessons of what we've learned and what is possible. So first of all, I'm just here to cheerlead and do the public face of UniProt. UniProt is a great team, and great data is only possible because there's lots of people working on it. So I'll talk a little bit about the SIB aspect of UniProt and how we look at things. So in biology, everything is connected. This is just the way it is. DNA is the blueprints, the RNA are the work orders, proteins are the things that actually do stuff. Then reactions are what proteins make happen as enzymes, and metabolites are the chemicals that we all eat and change and become part of our lives. And there are different projects. So the main project we work on is UniProt, which is associated projects like RIA for reactions and Swiss lipids for all the fats. Now, all of these are affected by disease because that's unfortunate reality. And as there's disease, there's hopefully a medicine. So these are the parts that we work on. HAMAP is a little bit of an example. It's a bit odd because it's not really a database. It's more of a database of rules about how to annotate proteins. So if you look at it today, you could actually go and download it, and you might find out that it's actually about 3,000 SPARQL queries as a rule, being used as a rule language. But it's not really the topic of today's talk. So what does this mean that everything's connected? Well, it means that we need to talk about our data in different ways. Because when we're doing research, our viewpoint changes all the time. And this means that we need to use graph data formats. It's kind of obvious in hindsight, but it has been a long journey to get here. So yeah, connections viewpoints, our data storage must support. So we're already kind of constrained to graphs because really a researcher might be looking at proteins, but he might be looking at it at a different viewpoint, different research angle than we would think of at UniProt. We also do a lot with the FAIR principles. And the first and most important FAIR principle is you must identify everything as well. Because F1, its principle is, of course, data are assigned globally unique and persistent identifiers. And we're not very good about that in the life sciences, to be honest. We have too many identifiers which are a little bit like our house in the middle of the street, where the street might have an identifier, but the pieces of impact inside not. So let me give you an example of this with our different file formats and different ages. So there's going to be a bit of diagrams coming up, where in blue, there's something that is actually F1. There's a global identifier, in our case, IRIs. Orange is like, well, we've defined an ad hoc graph implementation in a language or data format that doesn't have graph support, but and red is the blank nodes that are actually there in other data formats. So this is a little snippet of the flat file format. This was what was thought to be a great idea in 1986, and it's common with other databases like the European nucleotide databases. People like it because it's simple to parse. It's not quite true, but that seems to be the case. And in UniProt and in life sciences, everybody learned how to write parsers. This is why Perl was such a popular language for the bioinformatics field. So the things in red are things which should have an identifier globally, but don't. So the binding site here, well, it doesn't really have an identifier. The ligand doesn't have an identifier. The ligand superclass, that has an identifier, in this case with the Kabi ontology, and it will be a zinc finger. The echo codes, which are the way that we talk about evidences, they also have identifiers, as do the PubMed articles which we extract the data from. However, the pairing of this does not. It's properly a blank node. So this was what is 1986, and of course, 15 years later, XML came around. So again, lots of lack of identifiers. Only the ligand has one, the same way that it had before. And the evidences are gone because in XML, you can't talk about things like a graph. So the evidences are numbered and associated somewhere else in the entry. So it's an ad hoc, internally known graph serialization. Well, the future happened, and now everything has to be in JSON. And as you can see, we still have lots of blank nodes, which basically means things have an identity, but only from the context. Again, we have a new graph formalism because we don't really use PubMed the way that we use the echo codes. And the Kabi, as you can see, has two different representations depending on where it is. This is just how web developers seem to like to do it. So in RDF, of course, which you've been doing since 2004, almost everything is a globally unique identifier, and we use IRIs. We're still waiting for RDF 1.2, and we're really wishing that we can have something better than reification. But also the evidences work nicely, and they are very well to put in. So we don't have a problem with RDF meeting the FAIR principles because, to be honest, the FAIR principles were designed for RDF. They go hand in hand. And I want to go back to this because in the field, we see too many blank nodes. In many languages, you say, our blank nodes is an RDF thing that other concepts don't have. It's not something that is brought up as a concept in JSON, but it is. It's just there. Many things have identities, which is only contextual. So, as a tip, I would say, make identifiers as stable as possible, readable as possible, small as possible, rich as possible, and above all, they must be IRIs. There are other options, but in practice, IRIs are the only ones which are widely used. And why is this important? Because user experience goes down to the IRI level. This is true for something like computer assembly languages, to use the AT&T syntax or Intel. Well, flame wears away. For the OWL people, do you use a Turtle or Manchester visualization? And if you just do data on the large, Turtle or RDF XML, There's many pros and cons to each of these. And so you have to think about when you're designing your RI space, that user experience is important for this. Now, UniProt is not funded to hoard the data. We are funded to share the data. And it's all nice to share things, but nobody wants to participate in a big mess. So UniProt has to be very well organized and, like a museum, be very well curated. And because UniProt is very well curated, all the AI training in life sciences uses UniProt. So it comes to the FAIR parts again. Well, the last option, reusable, already implies that the data is usable. And for UniProt, we do have millions of users who use it. And we also have tens of thousands of people who use the RDF data directly, and more than 2,000 people who regularly write SPARQL queries on the UniProt dataset on the public side. And we know there's many people who have private copies internally. So in the life sciences, we need real interoperability. And we can't just say we do standards, because life science has a lot of standards, just like any other field. And we make standards with our friends and the people we know. But very often standards lack global options because they are just meant for small fields. And this leads to things like this. Here we have two standards for plugs, but they don't plug into each other. Well, both the socket and the power provider will say, we're standards compliant. And what do our users do? Well, they will write an ETL pipeline. And most of them will be as dangerous as this little example of converters. Because we all know how to do ETL pipelines. We all know how to write parsers. But we never really spend enough time on them. And all of them are lossy, and you will lose some data. And it's all the maintenance work to make sure that they remain updated. So we really can't force this to our users to keep on doing this. It's a waste of waste. And of course, our users will come back and they say, well, Google does something or Facebook does something, so should you. And that means that we start building in, high voltage lines equivalent of power cables, just because you wanted a little bit of something. That's, of course, very silly. But it's true. We all went into the big data craze. We all did Hadoop, Grid, and now microservices. We often look at the large corporations where things work at their scale, sensibly, but we can't actually bring those learnings and those lessons back to the level of a single PhD student or a small lab who also needs data. So when we think about our standards, we need to think more USB-C than power plugs. USB-C is by far a more complicated specification than any of the plug standards that you've seen in the slides. RDF is a little bit the same. It's more complicated than a simple text file. It's more complicated than an ad hoc JSON file. But once you have it, you can do so much more with it. And that we should encourage all the data providers to do. Because the standards that are applicable for high voltages or large corporations are not the ones which we need in our day-to-day life. Coming back to this idea of interoperability, and there are many graph serializations out there, but just graphs aren't the answers. You must connect the graphs, otherwise you still have the problems between intergroup dependencies. So we need semantic graphs, because that's the only way we talk about actual meaning, and also allow us to connect graphs from many different sources, which is why this entire topic of the cost action, distributed knowledge graphs, is so interesting, because this distribution part is critical. So we go to our world, and the current economic reality is no matter all the negatives, SPARQL and RDF are the only formats, the only data representations that actually allow knowledge representation on a global scale. because we don't have to have prior agreement and we can easily merge data on the fly. And the economic reality is extremely important. This is what we do in the bioinformatics, and we still do too often. You take a few public data sets, let's say the gene ontology and UniProt in XML, and you'll have some data of yourself, because of course you're doing your own research. JSON XML doesn't really matter. Database or Solr or anything else, same story. You'll have to multiple parsers, you'll have to deal with the schema, and you will have to load it in and put it in a very big data warehouse. There's nothing that has changed here in the last 20 years. In the RDF world, we already had ID. The schema is embedded in the data, so you can just load it. Doesn't really matter if it's in RDF XML, and triples, turtle, they're all very much convertible. So we still have the cost of your own schema, and you still have to deal with loading all the data. So expensive, but starting to be doable. Of course, since 2014, we have SPARQL 1.1, and we have built-in query federation. And now, for a researcher, they only need to pay for their own data, their own schema, and their own SPARQL endpoint. And then they combine it on the fly with as many SPARQL endpoints as they want. And on the economic side of how much this costs is a humongous reduction for the average small PhD student. We still once in a while get questions on our help desk for UniProt, like from a student who says, like, I'd like to have a SPARQL database of UniProt internally. And he will say, I just installed another terabyte of hard disk in my laptop. Will that be enough? Well, UniProt today, if you download in the XZ compressed RDF XML, which is really quite concise, is almost a terabyte in itself. And you haven't even loaded it into SPARQL endpoints. That's just UniProt, but you will need so many more data sets. How can a PhD student or a small lab afford this? They can't. If you want to have data analytics, you have to federate, you have to go distributed. So UniProt's been in production for 2014, and since then has been joined by some other smaller databases. So the current UniProt release is about 160 billion triples, which on disk is 10 terabytes with Virtuoso. We use VDO, so we have compressed disk space, so it's 5 terabytes that you actually need. For RIA, Swiss Lipids, and HAMAP, we use RDF4J because they're much smaller. Swiss Lipids looks very large for the size that it is, but that's just because we inserted all the images inside the SPARQL endpoint, because why not? It's so small. And we just did that as data URLs, which are a nice trick with FOV depicts. The nice thing about SPARQL endpoints is that we're not just alone. There is network effects. We have friends, and many of them are in our institute. Our institute is a bit different than you might imagine, because like many things in Switzerland, it's federated. So when I talk about a database called BG or string, they are in different cities and different universities. There's different firewalls between them. So even beforehand, where we always wanted to be able to query and cross-query across all our databases, we couldn't. It's only with SPARQL that we could, which is why more and more SPARQL endpoints are arriving. And keep attention to this list because it's going to grow. And we're not the only ones in the life sciences who provide it. This is a tool called YummyData, and it ranks SPARQL endpoints in the life sciences for how good they are. It's a very nice setup, and they are quite different in how they do the monitoring, and they do have a conservation about how to monitor, what makes sense, what kind of queries do they write, and what not. Because it's quite easy to give a humongous load on SPARQL endpoints just by doing monitoring. So this gives a very nice FAIR ranking. And as you can see, UniProt is quite high, and it goes up and down a little bit because of how fresh the data is. UniProt has a twice 2-monthly release cycle. So at the end of the 2-monthly release cycle, the score is a little bit lower than if a new one just goes out. So That's all very nice, but can you show me an example? Yes. This might be a question that a researcher has, and it's quite a unique one. Do you want to find the genes encoding enzymes, where the enzymes catalyze reactions, of which the metabolites, and find the drugs acting on these enzymes? Okay, let's try it with a SPARQL query. So the first one is quite simple. We look at UniProt, where you look for protein and disease. Okay. UniProt annotates genetically linked diseases. We do that ourselves. That's our curators who do this. So you go from an UniProt entry protein to a disease annotation, and a disease annotation will have a disease. And that disease then will be linked to other databases, such as online Mendelian Inheritance in Man, which is a database of diseases. We want the reactions, so the chemical reactions. So we correlate, we start our process to federate to RIA. So the first part is UniProt uses RIA, but it's only a subset of the data available. So again, we go from UniProt via annotation to the catalytic activity, and there we can find the catalyzed reaction, which is described in RIA. So here we start our first federated query. So here we start matching up reactions to metabolites. RIA is a database which uses an ontology called CABI for chemicals. And here we link these up in different ways. Okay. We also wanted the genes. In this case, we'll just use our cross-references to ensemble. That will give you the gene identifiers. But there's also a database called Campbell, where we have a very limited subset to in cross-references. But Campbell is a very interesting database because it's a database of drug targets and the tests that have been done with them. So here we start again going outside of our competence, outside of what UniProt does. Still related in the life sciences, but really no longer in our team. So we combine the activity where there's a molecule tested, which is drug, and the assay that was targeted on has a protein associated, which was the UniProt protein that we started with. So altogether, it makes a very large query. But interestingly enough, it uses many different databases. So it uses UniProt, it uses RIA, and these are co-hosted not too far away from each other. But the last one is this first federated service hosted in the Czech Republic by the Elixir node there, which has a SPARQL endpoint, which is much more focused on biochemistry than UniProt. So it's not the fastest query, but if you wait a bit, here we are. We have an answer. This shows that our data really is connected and is interoperable, and people can reuse it in ways that we didn't imagine. Because none of our databases were assembled to be able to answer that question directly. It was only the combination that made it possible. This wasn't possible when SPARQL 1.1 was just out, but these are really becoming very common things. And if you look at any of the other query languages around, you don't have this capability because you don't have this easy graph merging. So what we show is that gene, protein, disease reaction, metabolites, and drugs are all connected. And with this connection, we can answer questions that we didn't think were possible before. So going a little bit to the practical setups. So how does this work? Well, for us, we have a very large graph database, but that's not enough. We don't just plop Virtuoso there and that's it. Like everybody else, we use a firewall to make sure that we can act on low-level threats. We use Apache HTTPD for basically load balancing and logging, and also rewriting some of the Perl requests that you might have. And the Perl request, I mean, is for our IRIs. If you do content negotiations, you do the HTTP 14 dance and you get the right results. We also have some custom middleware that we write ourselves. And on the back end, we either Virtuoso for UniProt or RDF native for everything else. So what kind of service do you need to host UniProt SPARQL with thousands of users a day? Well, in 2014, when we went live, we had 64-core AMD Bulldozer machines. with a 1/4 terabyte of RAM and 8 terabytes of SATA 2. It's not actually true. We start with a little bit less, but later on we put bigger disks in. A decade later, we bought new machines, fewer cores, more RAM, and much more disk space. And if you look at it and you go actually to a vendor and ask, like, how expensive is this? Well, it's actually not so expensive. This is doable for a small research group. But on the other hand, imagine if our 1,000 users all needed to pay for it themselves. How many millions would the scientific community need to spend just to get the capability to do ad hoc queries once in a while? It's very rare. So why do we have custom middleware? Why did we put effort into it? One of the reasons was very simple. We never knew if Virtuoso was going to scale as well as it was. And there might always be a new implementation in backend that goes further. Also, when people take our SPARQL examples and bring it in-house, we want to make sure that it works, no matter what vendor they use. If they use Stardog, Oracle Exadata, AWS Neptune, our examples should work. We should be really standard compliant. So we always went with the option of double parsing the SPARQL queries. So we first parsed the SPARQL queries with RDF4J and soon also Jana, and only then, if both of these agree that it is a proper SPARQL query, we give it to Virtuoso. And if Virtuoso also agrees it's a proper SPARQL query, it's executed. That gives us the capability in the future to move on to a different implementation if required. The other option is, well, being a public endpoint, you get lots of traffic, and not all of the traffic is as nice as you might want it to be. We have lots of bots, and recently that has been going up a lot because all the GPT friends really seem to like the UniProt SPARQL endpoint and go at it quite a lot because some of the IRIs we use are only available in the SPARQL endpoints. All these bots tend to be actually not so nice. They do not set accept headers. They might get whatever they want, or actually the lowest common denominator, which often is the output of the scribe query. They don't pay attention to robots.txt because they just assume, well, I'm Google, I can do whatever I want. And that goes true for Cloud and Gemini as much as anything else. So we use the middleware to make sure that we do things in an efficient way. So we can rewrite queries and we can also change how they interact with our endpoint. Something that these bots might do, and this is also true for some of the monitoring bots, is they will come and they will ask for a counting query. Like, how many distinct predicates do you have? How many distinct IRIs do you have in the database? Well, if you take all the IRIs in UniProt, and you just line them up one after the other and put them in a flat file, single column, you're talking about a file which is about 8 terabytes in size. If you then use something like gnews sort to, get a distinct count, like you might do on command line, you might talk about, 2 weeks of processing time. Well, Virtuoso is a lot faster, but still too slow to do this real-time live. And there's lots of variations on this, so can't really blame the developers on that one. But the nice thing about UniProt is we are quite stable. So we know how many IRIs put them in, so we can just rewrite your SPARQL query and direct them to the information schema, which is basically a void file. It comes out of our service description. All these queries, of course, have different variations, but they're the same conceptual. Might be in variable usage, might be in using of prefixes or not. The nice thing that we do is we take the query algebra in RDF4J and we match the query algebra and then we rewrite. So we don't have to worry about variable renaming. We just keep on that being correct. So having said that, bots, we really don't care. The owners are absolutely not considerate and they don't pay attention to the standards. And for us, for example, in the last few months, we went from roughly 1 million bots requests per month. And now with ChatGPT is really liking the SPARQL endpoints, we're going between 7 and 14 million requests per month. So it's quite a big jump. And if you're not ready to interact with them, you have to be quite quick and change some things. That's why we needed our own middleware. And we couldn't just depend on our vendor to go implement things when we needed them. So I would like to close out with a little bit of a call to action, and that is semantics really scales. So especially in the semantics research groups, you should really use it a bit more. It's a pity when we talk about things like the linked open data diagram, where the backend really doesn't use semantics, which makes it very expensive for us to maintain. There's many crawlers, dataset collectors, and very few of them actually be able to crawl our side. You all expect us to push data, and at scale, that's really not affordable for a group like us to maintain. At this point, I would like to thank again the UniProt team for making it all possible. This is the current team across our 3 sites. If you don't have good data, you don't need a good SPARQL endpoint because it's not worth querying. So at this point, I'd like to say thank you for your time, and I'm open for questions.
So, thank you very much for your very interesting talk and for your insights. I can try to give you a virtual round of applause, which the noise cancelling of Zoom will kill. So let me give it a try. I don't know if you can hear it. I would have a few questions. Otherwise, I would invite everybody here on the stream to write them in the chat here. On the YouTube chat or here in the Zoom call that this stream is based on. And in the meantime, I can start with my own. You showed one picture about this USB-C figure, right?
Yes.
And I want to challenge your metaphor. In that way, I mean, the plug itself is easy, but I would say that RDF is that simple and can do one thing very well, namely to model triples and have a very flat kind of graph, whereas USB-C, you can have power in different scales, data fast and slow. So it's while the plug itself is more standardized, the content and everything is more can be anything. So in that sense, it's a complicated plug. Or how far does your metaphor go?
Well, metaphors always break, and in this case, it breaks quite quickly. But I really wanted to bring the point of USB-C is something that you will use in the house. And very often we look at data providers where the technology is used by a very large vendor. And then we get the jokes like, Google uses it. Yes, but Google has 40,000 software developers and a research budget that is as big as Horizon Europe. And you're a professor and you have 2 PhD students. Maybe that technology choice isn't adapted to your life. The other part is USB-C is more complicated than a standard power plug. And let me just rise one up if it comes up. I have to, yeah, that shows, you know, that was the technology of the 1870s. So things have migrated and moved on a bit. So our data formats can deal with a bit more complexity than we needed to deal with in the days of floppies.
Okay. There are some questions coming in. So here's one from Olaf. And he said that you briefly mentioned that you are waiting for RDF 1.2. And can you elaborate on that a bit more? Like, what are the features that you are looking forward to? What kind of complexity do you fear? And these other things.
Well, we submitted our use case for UniProt to the working group to be considered. And what we really wanted, and that doesn't mean that this is what we need. This is, it can be a better buggy, right? Is easier reification. And the first paper I wrote about UniProt, SPARQL, and RDF was about reification and how we used it. And that about 15% of our data in UniProt Knowledge Graph is reification triples. And all we really wanted was a keyword in the graph language which says reification, and then we didn't have to type out the 4 quads. So that's really basically still what we want. And IRIs can be represented many ways for the same concept. So we aren't so great with the transparency part, although I always get these confused, opaque and transparent. But yeah.
So the main thing would be like syntactic sugar to write.
Yes, yes.
Okay, cool.
Scientific sugar, but also syntactic sugar that does add a bit of constraint to the implementer, so that the semantics become more constrained and more things become possible. To take a little bit of an analogy, Java records. Java records are in some ways just semantic sugar for data classes. And these classes you could already write in Java. They were just annoying. So that wasn't really much added. But you also constrained a little bit what you could do. So now the whole state is represented by the record, and you can start doing lots of interesting things there. And I hope that the reification solution from RDF 1.2 will enable these kind of things as well. And I haven't really thought about them. I have written some stupid emails to the working group that I'm very happy were completely ignored. So I'm going to leave the working group to do their magic.
Okay, thank you. So you've talked about ETL pipelines a lot and all the mapping that is being done here. And I mean, there's a lot going on in terms of knowledge graph construction. So I was wondering, is there also like all these ODBA approaches or some R2RMLs or a bit more principled, or RML itself, more principled approaches to ETL? And are they still, would you still frown upon them, or?
No, not at all. But I also look at R2ML a little bit different. I don't just look at it as a mapping tool. The nice thing about RDF is that it separates the physical representation of your data and data store from your conceptual knowledge graph. So it's simple. It's something that's true for the formats itself. You can have your data in RDF XML or Turtle or JSON LD. In practical terms, sure, there's some ASCII codes which are in the lower numbers which don't transfer. You can take any RDF XML file and make a Turtle file. The physical representation on disk is independent. You're going to go to HTT or whatnot. But R2ML is, you can say, well, there's a lot of investment in making very fast relational databases. Can you go from a random RDF file to a relational schema? And Ori Erling and Van Duck did really early work on this, which was unfortunately never shipped in Virtuoso, where they would create a reasonable relational schema from a given RDF graph. And then you could still query with SPARQL because this translation layer existed. So I think R2RML is much more valuable in this kind of optimization steps than direct ETL pipelines, because in some ways, you no longer do the load in that case, right? You just do the transform on the query side, which is a really nice trick. And I'm really happy that it exists because it's really useful.
Okay. So you've talked about HTT already. So except for the SPARQL endpoint, do you have other endpoints like web, like dereferenceable URIs or triple pattern fragments or anything like that? Or yes or no for each of these options?
Yeah, so all our IRIs are dereferenceable. If they aren't, that would be a bug. They dereference either to HTML or different representations, depending on what IRI it is. For triple data fragments, we've looked at it, and triple pattern fragments, sorry. And it is a really nice technology. And it's really nice because it's not an either or, right? You can have TPF and SPARQL. You can run SPARQL on TPF. That's with the Communica framework. But why we didn't do it, why we didn't implement it for UniProt, is that it didn't make the difficult things that people want easy. It's very easy to ask a triple pattern fragment from UniProt, where the fragment is like 4 terabytes of data. And then the problem became quite big for the end user. Like, well, you first need to download thousands and thousands and thousands and thousands of triples just to be able to answer a query. So for us, hosting SPARQL was cheaper than triple fragments. But that's, of course, at what scale does it happen? And what kind of solutions do you have? TPF is fantastic for every researcher who needs to have a data preservation plan where they don't want to run infrastructure for 20 years. But once in a while, it'd be really nice if you could query your data that as you had it 15 years ago, relatively cheaply. And for those kind of researchers, TPF is great. And I really like the way that it complements each other.
Okay, cool. I would like to combine a few questions about the traffic that you get. So maybe you can give us some insights. So you said you have dereferenceable URIs. How much traffic do you get compared to SPARQL? And from that traffic that you get overall, which is legit or the bots?
No, the bots are also legit, I would say.
Okay.
But it's very hard to say because, for example, recently we had a user who sent us 175 million queries, and he wrote a little program and he looped over our database. I mean, if you have 250 million, identifiers to start with, you quite quickly get into humongous query numbers. Those queries could probably have been rewritten as a single query, but then the HTTP connection might have broken as well. So whatever was better, it's hard to say. What I would like to say is that on an average day, we have about 600 users who write their own SPARQL queries. And over a month, that's about 2,000. And we know they're real people because they go on holiday and they have stop in the weekends. And the kind of rate of query writing that is unique on the weekends is significantly less than in the normal weekday. We also have, like on a normal website, an uptake in September when people come back from holiday as academics. We see slightly increases. Christmas, big downfall. So yeah, it's hard to say because SPARQL queries can be very small, that they fit within the get character limit, like about 600 characters. But we also have ones which have, where the SPARQL query is larger than 2 megabytes, and we have to up our limits a few times already. So there's a big variety in what people do, and it doesn't really, it's hard to count in the same way that it would be for REST service. But even there, you see the same behaviors. When some people has to implement a join on the client side, well, he will still send 250 million REST requests. It'll still be one user doing the same thing as that SPARQL user just did. But yeah.
Okay. And when we talk about these Gen AI bots, so in the beginning, I mean, everybody was trying to get, I don't know, a limerick or whatever from ChatGPT about, or to transfer a letter to the style of the King James Bible or what. And
Yes.
at what point, and I don't know about the use cases for UniProt in that. So at what stage did like this traffic appear, and what is it about? Because for the lay user who needs to, I don't know, summarize a document, or that is interested in general knowledge or whatever, I guess, why should they go to ChatGPT and then ChatGPT come to you? So I was wondering if you can shed some lights about the use cases of this traffic that...
Oh, this is the training side. So this is the bots just going out and trying to download the internet in an inefficient way. and that's what
Okay.
they are. For the use cases, we see quite a lot of uptake, and my colleague Anna Claudia Sima at Vitalite and the Swiss Institute of Bioinformatics, but different group, has done quite a nice amount of work on using ChatGPT and equivalents to generate SPARQL queries. And I think there was a recent paper where it was very similar about using ontologies to validate the SPARQL query that came out of ChatGPT, which is excellent work, because ChatGPT will generate very valid SPARQL queries, especially for UniProt, which is quite well known apparently, and where it has seen a significant amount of turtle output of it as well. And you make pretty valid queries, but you will never get the identifiers right. So you might ask for a query which is about a certain bacteria, let's say E. coli, and no matter what you do, ChatGPT will put the tax identifier for human in it, because that's where most examples have. Well, the nice thing about the SPARQL output that you can get is you can parse it again. You can match it to the ontology, like Jen Sukada was the name that I was looking for, did recently. But you can also look at, well, use the predicate organism. So the thing on the right side should be a tax identifier for an organism. Did that match to anything in the original prompt? Yes, no. And there you can do reverse entity mapping between the prompt and the output. And then you can get really nice outputs, which making the query language SPARQL a lot easier on people to get started.
Okay, cool. So these bots during training time really write SPARQL queries, or they come via the dereferenceable URI?
Most of them come via the dereferenceable URIs.
Okay.
The vast majority.
Okay.
There might be a few which have clicked on the SPARQL examples.
Okay.
But as Turtle and SPARQL are so close, if you learn on Turtle, you've also kind of learned on SPARQL.
Sure.
Which is something you can try out. And I don't know if it still holds, because these things change all the time. But when I tried ChatGPT in the beginning, and you ask a query of UniProt, and you ask, can you give me the XPath? It was very much worse result than the equivalent with SPARQL. And I believe, and this is a belief, that this is the case because Turtle and SPARQL are so similar, and both of them are kind of similar in sentence form to normal English language.
Okay. We don't have too many questions lined up. There's one that I would like to, where that person could just, it's a question about software that you use, so we can just, that person can just get in touch via email, I guess. Otherwise, have you tried property graphs?
So I think we tried Neo4j about the same time we started on the RDF journey, but not us, our colleagues at EBI. And while in some ways it's an easier to write query languages than SPARQL Cypher, the fact that it has absolutely no network effect on the scale of actually allowing people to connect databases on the fly makes it kind of a useless thing. It's like a worse SQL. Because while the graph path things are important, most of our interest is things that would be very much expressible in SQL. So if the answer had been, could we have Neo4j and Cypher, or could we have had a MySQL database, our user base would have screamed MySQL really, really loudly. And Cypher and the previous approaches from Neo4j and others just didn't add anything there.
Okay.
So.
Cool. So, I don't get more questions in. If there's, we have a bit of a delay in the chat, so let's wait for a few seconds to get in more questions.
So I can quickly answer the one about the data catalog.
Yes.
And the data description is pure void, and it's in our service description for the SPARQL endpoint. And we think void should be used much more than it is. And I hope to get restarted and updated for the changes in RDF 1.2 and everything else that has happened since then, like shackle shapes. So,
and in terms of UI, what is it that you use?
Oh, we have our own custom UI.
Okay.
That is a problem when you start early in all these things. There are no community standards to go with, so we have more home written code than I'm happy with.
And in this home written code, you like look at the triples then from JavaScript or whatever and create a UI out of that.
Yeah, just
So
old-fashioned HTML templates, basically.
That thing that all the developers fear when they encounter RDF for the first time.
That is also true for all the other databases, to be honest. Yeah.
Good. Okay. So thank you very much again. Please stay on the call. I would like to do some housekeeping then for this talk series. Yeah, small round of applause from me again. And now I stop yours. Can you stop your sharing? And I will take over.
Yes, I did.
That was it for today. We continue after the summer break. You can check out our website. But who is this website by? Well, it's from our Cost Action. That is a research network with more than 30 countries represented. And we have one final call for STSM's short-term scientific missions, which can send you through Europe if you write a nice proposal and if you want to do short-term research somewhere else over the summer. Check out our website. There you'll find the necessary information on how to apply for that. Otherwise, this action ends in September 2024. And I guess there are some plans to continue some of the activities that we started, like this talk series. Otherwise, follow us on this thing formerly called Twitter. Cite and subscribe. You'll find all the recordings of our previous talks on our YouTube channel. And with that, I want to close the stream.